Hello, this is Gary Stapper. Today we'll be talking about radicals and rational exponents. So our objectives will be to evaluate square roots, to simplify expressions of the form square root of a to the second power, use the product rule to simplify square roots, add and subtract square roots, rationalize denominators, evaluate and perform operations with higher roots, and to understand and use rational exponents. Okay, we'll begin with the definition of the principal square root. Most of the times we'll just say square root, but why we call it the principal square root is because it's just to signify that anything that comes out or the result of a square root is positive. So never will be negative. So that's why we call it the principal square root. So in general, if b squared equals a, then b is the square root of a. Okay? So that would make b have to be positive. So if the square root of a equals b, then b must be positive. So the definition of the principal square root. If a is a non-negative real number and the non-negative number b, which means it can't be negative, such that b squared equals a is denoted as b equals the square root of a, is the principal square root of a. Okay, that's just like a restatement of the statement above it. So it's just basically saying the same thing. So let's look at a few examples. So example, if we evaluate a square root, for example, the square root of 81, the square root of 81 is 9. Now, 9 squared is 81. Now, I understand that if you square negative 9, if you square negative 9 times negative 9, it's also equal to 81, but recall, b must be positive. So, and negative 9 is not positive. So some people will say the square root of 81 is plus or minus 9. And that's not correct because we're talking about a principal square root. So even though negative 9 squared is also 81, the square root of 81 is only the positive portion of that. So it's only equal to 9. Now notice there's a negative on the outside of this one, negative square root of 9. So this is kind of like an order of operations. The square root symbol is kind of like a parenthesis. It's acting as a parenthesis. So you must take the square root of 9 first and then take the opposite of it. So the square root of 9 is 3 because 3 squared is 9. And then the negative just kind of has like an attachment to it. So it's going to be a negative 3. Now, when people see that, they think, well, negative 3 squared is not equal. Negative 3 squared is equals to 9 as well. Okay? But again, the negative that negative is being attached from the outside. So the square root of 9 is 3, and then the negative comes along with it. Now, evaluate the square root of 36 plus 64. Now, we're going to make a note of this in a minute, but I want you to look at the answer. 36 plus 64 is 100. So what they're trying to do is they're showing you that 36 plus 64 must be added first, and that's the square root of 100, because 36 plus 64 is 100. And then the square root of 100 is 10. And why is it 10? Because 10 squared is 100. Now notice again, it's the principal square roots. So even though negative 10 squared is also 100, principal square roots is referring to the positive portion of that. So the square root of 100 is 10. Another way you can check that to make sure is punch in the square root of 100 on your calculator. It doesn't give you two answers. It only gives you one. It only says the square root of 100 is 10. It doesn't say negative 10. So even the square root symbol that's on your calculator is also referring to a principal square root. We just get kind of lackadaisical sometimes and forget the word principal on it. But that's what it is. It's called a principal square root, and we just kind of shorten it to square roots. Now, I want to make a note of this. I want you to note that the square root of 36 plus 64, you cannot break up the 36 and the 64 into pieces. A lot of people will try to do this. They'll say, well, it's the square root of 36 plus the square root of 64. And the square root of 36 being 6 and the square root of 64 being 8, the answer they'll get sometimes is 14. But if you notice, that kind of flies in the face of the answer we got above that, because 10 is the answer. Okay, so we know it's 36 plus 64 is 100, and we know 14 does not equal 10. So what I haven't read there cannot be true. And I put a not equal sign because you cannot break it up into two pieces in that regard. So, in other words, the square root of a sum does not equal to the sum of the square roots. And that's just that proves it right then and there. So, okay. All right, simplifying expressions of the forms square root of a squared. For example, if you want to take the square root of a squared for any real number a, the square root of a squared must be equals to the absolute value of a. And you're like, well, of course, because they cancel each other out. But you got to be careful. Because look at a few of these things in a minute. It says, in the words, the principal square root of a squared is the absolute value of a. Now, what does the absolute value of a mean? It means the distance a is from 0. Well, what do we know about distance? Distance cannot be negative. So that's why the absolute value is there, is because a principal square root must be positive. So if you look at this, it says simplify the expression. The square root of 5 squared is equals to the absolute value of 5 by the explanation above there, and the absolute value of 5 is 5. Another way you could look at that is saying, well, 5 squared, what is 5 squared? Well, 5 squared is 25, and the square root of 25 is 5. So because 5 squared is 25. So that one is not that kind of makes sense there, but look at the next one. If you think the square root of negative 5 squared, some people think of it, oh, you just cancel the square root with the square out. If you do that in this case, the answer would be negative 5, but it's not. Because negative 5 squared is 25 as well, and the square root of 25 is 5. That is the example of why you have to put the absolute values around it. So yes, the square root and the square cancels, but absolute value to force the number to be positive. So that's what the absolute value is placed there, whether it's 5 squared or negative 5 squared. That's why the absolute value is there. It's just a reminder that the principal square root is being invoked here. Okay, so that's why it's 20. But it makes sense that because it's the square root of 5 squared is square root of 25, and the square root of a negative 5 squared is also the square root of 25. Both of those answers are 5. So just basically what I want to impart here is that when you take the square root of something, it can be 0, but it cannot be negative. So it could be a positive number or 0, but never a negative number, because we're talking about a principal square root. Now, let's look at the product of square roots. If you recall a while ago on a previous slide, we said that the square root of a sum does not equal to the sum of the square roots. Remember, we had the square root of 36 plus 64, and we said we can't break that into the square root of 36 plus the square root of 64 because we would get 14, and the answer was 10. Remember that? Well, this one is the product rule of square roots, and you can break these up. So if a and b are representing non-negative real numbers, then the square root of ab can be broken up as a product of each square root. So the square root of ab is equal to the square root of a times the square root of b. And the second equation there is the same thing, but written in the other direction. The square root of a times the square root of b is equal to the square root of ab. So of course, if the first one's true, the second one has to be true by what we call the symmetry property. So simplify the expression square root of 75. Now look at this one. Now you're like, how can you simplify that? Because 75 is not a perfect square. I mean, the square root of 81, which is bigger than 75, square root of 81 is 9. And the square root of 64, which is smaller than 75, is 8. But 64 and 81 are perfect squares. 75 is not. So if you were saying, well, square root of 75, how can you simplify that? All I can tell you right now, I know it's somewhere between 8 and 9. But I can break it down into smaller square roots, because 75 is the same thing as 25 times 3. And you're like, well, why did they choose 25 times 3? Because 75 is also 15 times 5. So why didn't they, instead of using 25 times 3, why didn't they use 15 times 5? If you said because 15 times 5, neither of those numbers are perfect squares, then you'd be right. In this case, 25 times 3, 25 is a perfect square. That's the reason they chose 25 times 3, because what they're doing is they're searching for factors of 75 that are perfect squares. 25 is a factor of 75, and it is a perfect square. So it's square root of 25 times 3, and so square root of 25 times 3, you can break that up by the property above that, the product rule. And so it's the square root of 25 times the square root of 3. And the square root of 25, remember, is 5, and the square root of 3 is the square root of 3. So it's 5 root 3. So this is what some people call, excuse me, as just reducing the squares out of there, just basically put it in a reduction form. It's, well, what happens if you punch square root of 75 onto your calculator? Yeah, you'll get somewhere between 8 and 9. But you know what? If you punch in 5 times the square root of 3 into your calculator, you'll get a number between 8 and 9 as well. As a matter of fact, it will be the same number. So square root of 75 and 5 root 3 are the same numbers, except the only thing is 5 root 3 has no more perfect squares within the square root. That's why we call it simplifying the expression. So, but the bottom line is the numbers are exactly the same value. Now here's another one. Okay, so we have the square root of 5x times the square root of 10x. Alrighty? And the square root of 5 times the square root of, now we put those together. So 5 times 10 is 50, and then x times x is x squared. Now, 50x squared, what we're going to do is look for the factors that are perfect squares. And of course, x squared is a perfect square. And 50 is 25 times 2. So they put 25 and x squared together because both of those numbers are perfect squares. Square root of 25 is 5, and square root of x squared is x. So we break those up into separate pieces. The square root of 25 times the square root of x squared times the square root of 2. The square root of 25 is 5. The square root of x squared is x. And the square root of 2 is the square root of 2. Now, there is one problem with that, and it's the square root of x squared being x. Now remember, x cannot be, when you take the square root of something, the answer cannot be negative. So what if x was negative to begin with? Then 5x square root of 2 would be negative, and we can't have that. So to make this more correct, the author here kind of messed up a little bit. This should be 5 times the absolute value of x times the square root of 2. So you might, when you're taking notes, and you should always take notes when you are looking at these videos. So if you're not taking notes, it's like looking at a movie and being asked about the movie 3 weeks later and a small nuance of the movie, and you can't answer because you don't remember what was said. This is the same thing. So it's like when you're doing your homework, you're going to be asked questions to do problems, and if you're taking notes, you got something to refer back to. So just a reminder for this video and any video that comes after this, when you're watching them, take notes. It's like being in a classroom. Okay, you wouldn't go into a classroom and listen to an instructor give you lecture notes on the board for an hour and a half and not take notes. And this is the same thing. You need to be taking notes through this whole process. So when you're taking notes here, you need to make sure you put absolute value of x on that last number. So, and maybe make yourself a note that says, in the video, this did not have the absolute value in it, but it should have it. And that would be an extra reminder that that you need absolute values on those. You're like, well, I didn't have absolute values on the previous problem because 5 root 3 is already positive. There's no variables involved. So there's no way that can be negative to begin with. But in the second one, x, if it was x, was a negative number to begin with, but you don't know what x is. X could be 4, but that would be okay. But if x was negative 3, then you got a negative number, and that's a problem. But anyway, that's that expression. Now there's a quotient rule of square roots. Now notice we had a product rule, and we have a quotient rule of square roots. So if a and b represent non-negative real numbers, and b does not equal 0, and I'm going to go why does b not equal to 0, but what does that mean? Well, if you have the square root of a over b, then that equals the square root of a divided by the square root of b. And the second equation is the same thing, but using the symmetry property. Square root of a divided by the square root of b is equals to the square root of a over b. Now, why is it saying b cannot be 0? Because if b was 0, you'd be dividing by 0, and that means that would be undefined. Remember, you cannot divide a quantity by 0. You can't divide something by 0 parts, in other words. And if you don't believe it, try it on your calculator. Hit 8 divided by 0, 7 divided by 3 divided by 0, -4 divided by 0. It's undefined. Because you're basically dividing, if you have 4 divided by 0, you're dividing 4 into 0 parts. And that means you're going to have an infinite number of possibilities there. And so therefore, there is no result for that. So if you tried it on your calculator, it would just say math error or domain error, depending on what kind of calculator you have. Okay, let's look at an example from this one. So if I have the square root of 25 over 16, that's going to be the square root of 25 divided by the square root of 16, which is square root of 25 is 5, and the square root of 16 is 4. Let's look at another one. The square root of 150x cubed over the square root of 2x. Well, if we put them together under the same radical, we'll have the square root of 150x cubed over 2x, and then reduce that fraction. And sometimes you can't do this, but this one you can. 150 divided by 2 is 75, and x cubed divided by x is x squared. Now, do you remember why that's x squared? Remember, x cubed is x times x times x. X on the bottom is 1. So you have 3 factors of x on the top, 1 factor of x on the bottom, so that cancels out, but there's still 2 factors of x on the top. So that's why it's 75x squared. Okay? And again, 75 can be broken down as 25 times 3. So that's why there's a square root of 25 and a square root of 3 on that next step. And then x squared is already a perfect square. So the square root of 25 is 5, and the square root of x squared is x, and the square root of 3 equals the square root of 3. So if you notice, they're breaking it up into individual square roots because you can, because of the product rule of square roots. And then they're just taking each one that's a perfect square, and then each one that is not a perfect square, and putting it off to the side. So now, do you see a problem? Yeah, it's the same problem we had a while ago. They need those absolute values around that x. Unless you tell me x is already positive. Sometimes they'll tell you that, by the way. Sometimes you don't have to deal with the absolute values around the x at the end, because they'll tell you in the instructions, simplify this, assume x is positive. And if that's the case, then you know when you took the square root of x squared, it's positive already because x is positive because it was told to you. Okay, but in this case, they didn't tell me x was positive. Now, they may be making that assumption, but they are not telling me that. So to make this problem here truly correct answer, you need to have the final answer as 5, absolute value of x, times the square root of 3. Okay? And again, you might want to put that in your notes that you should be taking to signify that. Okay? And again, I would make a note of that somewhere in the margins. Make sure that your answer is positive, because you don't know what x is. X could be a positive number, or it could be a negative number. And then if x happens to be a negative number, it's contradicting your principal square root concept. Because whatever comes out of a square root can only be positive. And not knowing what x is here in this final answer, then it could be negative. Now again, the previous example, the answer 5 over 4, there's no variables involved there. 5 over 4 we know to be positive. Okay, it cannot be anything else. So 5 is 5, 4 is 4, both are positive. So, okay, so let's move on a little further. Now we're going to add and subtract square roots. So 2 or more square roots can be combined using the distributive property, provided they have the same radicand. Now, you're like, what is a radicand? The radicand is the quantity or the number or the expression, whatever you want to call it, inside the radical. So if you have the square root of 17x, then 17x is the radicand. So whatever's inside. Remember the previous problem on the first example we did, the square root of 36 plus 64, then 36 plus 64 is the radicand. Okay, it's the number inside the radical. Anyway, so such radicals are called like radicals. So what that basically means is the radicand is exactly the same thing. then they're like radicals. If they're not like radicals, or you can't make them to be like radicals, then you can't combine them. It's like adding a plus b. What is a plus b? Well, a plus b is a plus b. You can't really simplify that because they're not like terms. Well, like radicals can only be combined if they're like radicals. So like radicals can be combined, like terms can be combined. So you replace the word terms with radicals here, and you got the same concept. So simplify the expression. 8 square root of 13 plus 9 square root of 13. Now, if I ask you guys what is 8x plus 9x, I would venture to guess that most people would say 17x, because 8x's and 9x's combines to be 17x's, right? You know, if you have 8a plus 9a, you have 17a. 8 apples plus 9 apples is 17 apples. So 8 whatever plus 9 same whatever is 17 whatever. Okay, so this is kind of what's going on. Square root of 13 is the same on both of those terms. So you factor out that square root of 13, add the 8 and 9 together, and you'll have 17 square root of 13. And that's it. I mean, square root of 13 cannot be anything. 13 does not have any factors other than 13 and 1. And neither of those numbers are perfect squares. So 13 cannot be broken down any further than that. So that's why that is our final answer there, 17 root 13. Okay, let's look at another one. Okay, the square root of 17x minus 20 square root of 17x. So square root of 17x matches on both of them. So we factor that out, and then we have 1 minus 20. You might want to know, where's that 1 coming from? Well, that square root of 17x does not have a coefficient in front of it. So when I factor that square root of 17x out, there's still a term there that's understood that every term has if there's no coefficient, a 1. I mean, after all, if you had x, what's the coefficient in front of an x? Well, it's easy to answer the question if I said, what's the coefficient of a 2x? Then everybody would say, oh, it's 2. What's the coefficient of 5y? Oh, it's 5. But when it's like z, and I don't say any coefficient in front of it, it's understood to be a 1. Well, it's the same thing here. Square root of 17x, there's an understood 1 in front of that radical. Okay, so when you took the square root of 17x out, the 1 minus 20 remains. And then 1 minus 20, of course, is negative 19. So the final answer is negative 19, the square root of 17x. Okay? Okay, our next objective here is to rationalize denominators. All right? So let's look at the process. The process of rewriting a radical expression as an equivalent expression in which the denominator no longer contains any radicals is called rationalizing the denominator. So if the denominator consists of the square root of a natural number that is not a perfect square, multiply the numerator and the denominator by the smallest number possible, okay, that produces the to a square root of a perfect square in the denominator. So for example, if you have the square root of, let's say, 6, okay, so if you have the square root of 6, well, if I multiply 6 times 2, that's 12, that's not perfect square. 3, that's 18, that's not a perfect square. I would have to go all the way to what to make it a perfect square? 6. Because what's the square root of 6 times the square root of 6? That's the square root of 36. And that is a perfect square. So 6 would be the perfect one. So what they're saying is multiply the numerator and the denominator by the smallest number that produces the square root that's a perfect square. Okay? Now let's say if it was the square root of 18 on the bottom. Well, then you would multiply the top and bottom by the square root of 2. Being like, why is that? Well, because square root of 18 times the square root of 2 is also the square root of 36. So depending on what that number in the denominator is, that's how you rationalize it. Okay? So that's the idea. That's why what we call rationalizing the denominator. Then I'm going to talk about the motivation of why you would want to do that. But let's talk about the process first. Radical expressions that involve the sum and differences of the same two terms are called conjugates. So if you have let's say you have the square root of a plus b, then the conjugate would be a square root of a minus b. Now, these numbers are not opposites, because if you want to know what the opposite of square root of a plus the square root of b, then it would be negative a minus the square root of b. You'd have to take the opposite of both terms. So conjugates are not opposites. Okay, opposites is taking the opposite sign of every term in the expression. Okay, the conjugates means you have two terms. You only take the opposite of the second term. So the square root of a plus the square root of b, the opposite of the square root of b is negative square root of b. The first term stays the same. Those are called conjugates. And you're like, what does this have to do with rationalizing the denominator? Sometimes you have to multiply the top and the bottom by the conjugate of the denominator to get rid of the radical in the bottom. And we'll show an example of that in a minute. But anyway, those are conjugates. If the denominator contains two terms with one or more square roots, multiply the numerator and denominator by the conjugate of the denominator. Okay? Now, the thing is, why would you want to be able to know how to do this? This is the biggest question. Even mathematicians kind of disagree on why you would want to do that. Some mathematicians, you ask, well, why do you rationalize the denominator in the first place? And sometimes you'll get the answer because you're told to. It's not good enough for me. Okay? Square roots in the denominator, they'll say, well, it's not simplified. What do you mean it's not simplified? Okay? You're just basically getting rid of the radical out of the bottom and putting it on the top. That's just another form of the same thing. Okay? And that's an argument. Now, the reason people will say to rationalize the denominator is because of estimation. Okay? Estimation is the big reason why we know how to rationalize denominators. For example, if you have 1 divided by the square root of 2, and I ask you, what is the decimal approximation for that without using your calculator? Okay? So, what is 1 divided by the square root of 2? Well, I don't know. Because you're like, well, square root of 2 is about 1.4, if you know that. So 1 divided by the square root of 2 is 1 divided by 1.4. Okay? All right? That's what it is. Now, what does that answer equal to as a decimal? That's when you get stuck. Okay? So I don't know what 1 divided by 1.4 without my calculator. However, if you rationalize the denominator from 1 divided by the square root of 2, and what it would equal to would be would be square root of 2 divided by 2. What is the square root of 2 divided by 2? Well, again, the square root of 2 is 1.4, and 1.4 divided by 2 is 0.7. So 1 divided by the square root of 2 is the same thing as the square root of 2 divided by 2. I'll show you how to do that in a minute. But square root of 2 divided by 2 is actually 0.7. So it's because it's easier to estimate when numbers or when radicals are not in the denominator. Okay? Now, an argument against that reasoning would be, well, what if I don't know what the square root of 2 is in the first place? Okay? Because how many of you guys knew what the square root of 2 equal to? I would suspect some of you guys would raise your hand. But not everybody knows what the square root of 2 is in the first place. Okay? And remember, square root of 2 is about 1.4 because 1.4 times itself is close. It's only an estimate, guys. So the square root of 2 is about 1.4 something. Okay? So it's close to that number. So it's an estimate. So the bottom line is, if you know some perfect square roots, like a square root of 2 or the square root of 3, some of you guys may or may not know what the square root of 3 is approximately, but the reason you rationalize the denominators of a fraction is for estimation purposes. Otherwise, you don't really need to know how to do this, but sometimes we want to know what the estimate is. So, and for some people, they will say, well, it just looks better. the radicals in the top looks better than them being on the bottom. So that's some of people's answer to that question. I don't like that answer. So, math, it looks good no matter which way you write it. If it's square in the bottom, square in the top, that to me doesn't really matter, okay? But it's for estimation purposes, and that is the reason we're going to do it, okay? So it's because it's going to be easier to estimate. All right. So let's look at how this works, okay? If you want to rationalize the denominator, see what I'm saying? Some people see 5 divided by the square root of 3, and they say that just doesn't look very good, okay? The radical in the bottom. So, but let's see how we do it. Now, what can we do to the 3, or multiply the square root of 3 by, to get a perfect square? Well, square root of 3 times the square root of 3 is square root of 9. And we know the square root of 9 is 3. So 9 is a perfect square. So let's look at that. So if you take 5 over root 3 and multiply the top and bottom by the square root of 3, and you're like, why can you do that? Well, sure you can. Because what's the square root of 3 divided by the square root of 3? Oh, that's 1. Multiplying by 1 doesn't change anything. So you can do that because the top and bottom is the same number. And if they're the same number, it's 1, and multiplying by 1 changes nothing. It's the identity property, basically. Anything times 1 is itself. Okay? So it doesn't change anything. Now, if you multiply that on out, you'll get 5 root 3 on top, and then the square root of 3 times the square root of 3 is the square root of 9. And then the square root of 9 is 3. Now, notice the 5 root 3 is now on top. So you don't change the value of it. So what I began with is 5 over root 3, and what I ended with is 5 root 3 over 3. So, and to be quite honest with you guys, the further you get into math, the less people are concerned about that, with radicals in the bottom. It's more of a formal thing than anything else. They want you to know how to do it, okay? And sometimes when you get into trig, you don't like the radicals in the bottom because of the exact answer problems, and so you deal with them so often that you want to put the radicals in top. But when you get beyond that, nobody really cares if they're on the top or the bottom. So for right now, just think of it as something you got to learn how to do just to get through it. So, all right, rationalize this denominator. Notice, okay, 8 over 4 plus radical 5. Now, you can't multiply just 4 plus radical 5 by just some single number to get rid of. You're like, what about square root of 5? Because square root of 5 times the square root of 5 is the square root of 25. That's not going to work, because if you just multiply by the square root of 5, the 4 has to be multiplied by the square root of 5 as well. So you'd get 4 times the square root of 5 plus the square root of 25, and that won't help because the radical is still down there. So what do? Well, we're going to multiply the top and the bottom by the conjugate of the denominator. This kind of makes it like a difference of squares. I mean, do you remember what a plus b times a minus b is? Those are conjugates. And you get a squared minus b squared. So that's a difference of squares. That's what makes this makes it a difference of squares. So let's go to the next step. So 8 times 4 minus radical 5. We didn't do anything with that on the top. Just left it alone for right now. And we got 4 plus radical 5, 4 minus. So we put the two fractions together. So there's nothing really I did here. I just put the two fractions into one fraction. Then 4 minus 8, 8 minus 4 minus radical 5. Now the top is the same, but the bottom is 4 times 4 is 16, so it's 4 squared. And then minus radical 5 squared. So those look like a plus b times a minus b is a squared minus b squared. Difference of squares. So the top is still 8 times 4 minus radical 5. Now 4 squared is 16. The square root of 5 squared is square root of 25, which is 5. So it's 16 minus 5 on the bottom. Now we have 8 times 4 minus radical 5. Now if you notice, they're not bothering to multiply that out until at the very end. I'm not really sure why he's doing that. I mean, you could multiply that 8 through in 2 steps above it. So you could say 8 times 4 is 32, and then 8 times radical 5 is 8 radical 5. He could have done that 3 steps up. I'm not sure why he didn't do it above that, but he just kept carrying the 8 times 4 minus radical 5 down 3 times. And then, of course, 16 minus 5 is 11. And then he finally distributes the 8. And 8 times 4 is 32 minus 8 radical 5 over 11. All that just to get rid of the radical in the denominator. If you notice, on the first problem, we had no radical in the denominator, right? But where did the radical go? The radical went up into the numerator. Same thing happened down here at the bottom problem. Yeah, you got rid of that 4 plus radical. You got rid of that radical 5 on the bottom, but you paid for it because you had 32 minus 8 radical 5 on top, divided by 11. Now, if you remember what I was saying a while ago about the estimation of that, if you try to estimate that one, you're going to have some obstacles as well. So, what is the square root of 5? Oh, I don't know, about 2.2 or something like that. If I'm right, I'm not sure if I'm right there or not. I think it's like 2.24. Then you got to multiply that by 8, and then you got to subtract 32 minus that number, and then divide that number by 11. Okay? All in the name of estimation. Okay? And it can be done. And if I had to do it, I would rather do that than try to estimate 8 over 4 plus radical 5 because the decimal's in the denominator. It's easier to divide by 11 than to divide by 4 plus radical 5. That's the bottom line here. So a lot of people say, well, can't you just use a calculator on those? Yeah, but you could use a calculator on the first one as well. Because remember, 8 divided by 4 plus radical 5 is the same thing as 32 minus 8 radical 5 divided by 11. All these are the same number. It's just a different form of the same number. So the first form has the radical in the bottom, the square root of 5, and the final answer, the square root of 5 in the final answer, but it's on top. But it's all in the name of estimation. So that's why I'm not a big fan of this. I'll be honest with you. I'm not a big fan of rationalizing denominators. I got to show it to you because that's what the book is. A lot of times they're going to be wanting the answer in the form of, and that's what you're going to need to know how to do. So it's just a way to write a number in this form a different way. So okay, let's move on. Okay, the definition of the principal nth root of a real number. So if you have the nth root of a equals b, that means that b to the nth equals a. Now you're like, well, wait a minute, this is the nth root. We was talking about square roots just now. Now we're in the nth roots? Yeah. These same roots can be, they could be third roots, it could be fourth roots, it could be fifth roots. So the ones that we've been doing up to this point are square roots. So the root was 2. So if you go to a higher root, like a third root, n would be 3. Okay? If you go to a fourth root, n would be 4. So if n, which is called the index, is even, then a is a non-negative, a greater than or equal to 0, and b is also non-negative, b greater than or equal to 0. If n is odd, like you're doing an odd root, a third root, or a fifth root, for example, a and b can be any of the real numbers you want them to be. Okay? But the symbol, the nth root symbol, is called the radical, and the expression under the radical is still called the radicand. So we're still talking about radicand. So if n is odd, the nth root of a is equals to, it should say a to the nth. So the nth root of a to the nth is a, and the nth root of a to the a to the nth. I think that the author made a mistake there. It should say the nth root of a to the nth is a, and the nth root of a to the nth on an even root is the absolute value of a. So I believe they're missing the nth root symbol, the nth power inside those radical symbols. So they made a mistake there. So for all real numbers a and b, where the indicator roots represent real numbers, if you have the nth root of a times b, it's the same as what they were when they were with square roots. The nth root of a times the nth root of b is the nth root of ab, and you can turn it around. Nth root of ab is equals to the nth root of a times the nth root of b. So you can say it either way. It's because it's a symmetry property again, and it works with the quotients too. So if you notice, we have we have you can break these things up if they're multiplication, and that's the product rule, and you can break them up into individual roots when there's a quotient, like the second one here, okay? But notice you can't really do that when they're adding or subtracting. Remember that very first thing in this video is I said the square root of 36 plus 64 cannot be broken up as the square root of 36 plus the square root of 64 because you get 14, and we know the answer is to be 10. So you can't break them up if they are sums. And you cannot break them up if they're differences. But you can break them up if they're multiplications or divisions. Okay, let's look at an example. Simplifying, multiplying, and dividing higher roots. So if we try to simplify the expression, the cube root of 40, and you're like, what do you do here? 40 is not a perfect cube. It isn't. Okay? So, I mean, there's not a number that you can multiply 3 times that would give you 40 that is precise or exact. But can we figure out some factors of 40 that are perfect cubes? Not perfect squares, but perfect cubes. Okay? So I understand 40 has a perfect square root. The square root of 4 times the square root of 10. But this is not a square root. This is a cube root. So here we're going to be looking for perfect cubes instead. Okay? So what are some perfect cubes? Well, one's a perfect cube, of course. What's the next perfect cube? Well, 2 cubed is 8. So the cube root of 8, what's the cube root of 8? Oh, it's 2. Why? Because 2 to the third is 8. Okay? But is 8 a factor of 40? You bet. So 40 can be broken down as the cube root of 8 times the cube root of 5. Because remember, you can break them up into 2 pieces. And because 8 times 5 is 40. But the cube root of 5 has no more factors that are perfect cubes. So I can't really do anything else with that. But the cube root of 8, I can. Cube root of 8 is 2. So you have 2 cube root of 5. Notice the cube root of 8 was simplified to just 2. And the cube root of 5 was just untouched. So it's 2 times root 5. Now, what's the difference? I mean, the cube root of 40 and 2 cube root of 5. Value-wise, there is no difference. If you have the cube root button on your calculator, and you do, you take the cube root of 40 on it, and you take 2 times the cube root of 5, decimal for decimal, all the way to all 10 digits or 8 digits, whatever you have on your calculator, will be precise every step of the way. Every decimal place of the way, they will be the exact same number. So cube root of 40 and 2 cube root of 5 has that same value. Why do we care to write it as 2 cube root of 5? Because we're breaking down, we're simplifying out perfect cubes. Cube root of 8 is a perfect cube. So again, it's about form. Okay, it's about the form of the number. Okay, let's look at another one. Simplify the cube root of 125 over 27. We can break this up into 2 numbers. Now, cube root of 125 over the cube root of 27. Now, if you notice, the answer was 5/3. You're like, how did we know that so quickly? Well, because 125 is a perfect cube. You're like, why is that? Well, because 5 cubed is 5 times 5 is 25 times 5 again. The third factor of 5 would make it 125. So the cube root of 125 is 5. So that one's actually pretty easy because there's not another factor to contend with. A lot of times, though, that 125 would be a number like 250. So then you'd have to get 250 and break it as the cube root of 125 times the cube root of 2. Now the cube root of 125 is the 3, but the cube root of 2 has to be left alone. So actually this one's a little easier because we don't have another factor that's big, makes the number bigger to contend with. Now the cube root of 27, well, as you could probably guess, it's 3 cubed is 27. So the cube root of 27 is 3 because 3 cubed is 27. So yeah, if you took the cube root of 125 over 27 on your calculator, you would get 1.66666666. But if you get 5/3 on your calculator, you would get 1.66666666. It's the same number. Okay? So these are the same value. Again, this is just about simplification. It's about the form of the number. It's kind of like when you were in grade school and you were getting 2/4 and your teacher said, Do you leave your answer as 2/4? No, you can't leave it in 2/4. You have to reduce your answer. You have to simplify your answer from 2/4 to 1/2. Now, if you put 2 divided by 4 in your calculator, it says 0.5. If you get 1 divided by 2 in your calculator, you get 0.5. So, value-wise, 2/4 and 1/2, there's no difference. What the difference is 1/2 is written in simplified form. And that's all it is. So, all right. Now let's look at the definition of a to the m over n power. So if the nth root of a represents a real number and m over n is a positive rational number, n greater than or equal to 2, then if you have a to the m over n power, that is equals to the nth root of a, and then raise that to a power of m. Okay, or you can put the power inside. You can also say a to the m over n is equals to the a to the m power divided by the taken to the nth root. Now, a lot of people have trouble with this one. Okay, let me explain to you in a little bit more of a country style way, I guess. Where do you find roots? I'm talking about tree roots or flower roots or grass roots underneath the ground, right? So look at that m over n. Think of the bar as the ground. The root is underneath it. Where's what's underneath it? It's the n. So think of it as a root of a tree, okay, or a root of a flower. So the n represents the root of the fractional exponent. So you have a fractional exponent. So a to the m over n power. The n is representing the root and the m is representing the power. Now, power. Well, the sun gives us power, okay? So the m is on top, above the ground where it can get the sunlight. So m is represented by the power because the sun's up above the ground. So that's why, how I remember it. I know it's silly, but I look at things sometimes odd way anyway. But the thing that's underneath the rational exponent, when I say rational exponent, I mean it's a fraction. So m over n is the exponent, and it's a rational number, a fraction in other words. And the bottom number in that fraction represents the root, because it's underneath the bar, it's underneath the ground, and the m is represented by the power, because it's above the ground where the sun's at. So anyway, that's the way I remembered it, and I hope that helps you. Furthermore, if a to the negative m over n power, it's the same thing, is a non-zero real number, then that would equal to 1 over m over n power. This is the negative exponent rule. Okay, so if you have an exponent that's negative, like m over n is in this case, then it's 1 over that. It's kind of like using the negative exponent rule, a to the negative 1. A to the negative 1 equals 1 over a. So those are the same thing. So let's look at an example of this. 27 to the 4/3 power. Okay, so the exponent is 4/3. So the 3 is the root, right? Because it's underneath, and the 4 is the power, because it's above the ground where the sun's at. So I'll take the cube root of 27 first. Okay, and that's 3. And then you take 3 to the 4th power. So you've taken care of the root. Now you got to take it to a power of 4. So 3 to the 4th power is 81. Because 3 times 3 is 9. Times 3 again is 27. Times the 4th time is 81. Now you're like, yeah, but can't you do this another way? You remember above it says also a to the m over n power is also, you can take the power first and then take the root. I probably wouldn't suggest doing it that way, and I'll tell you why. If you try to just take the 27 and take it to the 4th power first, you're going to have a very, very, very large number. So you'd have to take 27 to the 4th power first, which is huge, and then you got to worry about taking the cube root of that very large number. And the answer would be 81, but it's going to be really large to figure that out. So bottom line is don't do the also part. Do the top one. Take roots first, and then whatever that is, then worry about the power later. Okay? Powers after roots. But you can do powers before roots. It's just like this one I was just showing you, 27 to the fourth power. Well, you have to multiply 27 times itself 4 times. I mean, 27 times 27 is like 729. So 27 to the fourth power is basically 729 times 729, which I don't even know what that is. Okay? It's a really large number. Okay? So, but whatever that number is, take the third root, it's 81. So this is the way to go. Take the root first, which is 3, and then take 3 to the fourth power. Okay? All right. Next example here. Simplify expressions with rational exponents. So simplify using properties of exponents. So this is just basically some basic operations with exponents. So if we do this, 2 times x to the 4 thirds times 2 times x to the 8 thirds. So we multiply the coefficients, 2 times 5, put those together, and x to the 4 thirds times x to the 8 thirds. And of course 2 times 5 is 10. And then look at this, x to the 4 thirds times x to the 8 thirds. What are they doing there? They're adding the exponents. Isn't that the product rule of exponents? A to the m times a to the n. Should have picked that up in Math 103. A to the m times a to the n is a to the m plus n. You add their exponents. So you add 4 thirds plus 8 thirds, which by the way is going to be 12 thirds. So, and then 12 thirds, of course, is 4. So, notice once I got 2 times 5 is 10, I just kind of left it there and just kind of kept that attachment as I went down it. But it was just, the hard part of this problem is figuring out what x to the 4 thirds times x to the 8 thirds is. You add their exponents, 4 thirds plus 8 thirds is 12 thirds, because 4 plus 8 is 12. And then the denominator stays the same. It's not 12 sixths or 12 ninths. We got to remember how to add fractions. Keep the denominator the same and then add the numerators. So 4 plus 8 is 12 divided by 3, and that's going to be 4. Okay? So that concludes this section. Okay? This is P3 in this course book. May call it something else later on in a different course, but this is got to do mostly with radicals, rationalizing denominators and figuring out what square roots and cube roots are. Okay, I'm hoping that this is reviewed for most of you guys. If not, if it's not reviewed, if you're just learning it for the first time, I'm hopeful this is helpful to you. But most videos will last about this long, and I'm hoping you're taking notes. So what I need from you guys, if you're watching this video up to this point, I need you guys to go back and look at every slide. And if you don't listen to me when I'm talking to these videos, I want you to get each slide, write the problems down like they were problems written on the whiteboard in a classroom setting. Okay? When you're doing that, you're learning the things, learning the concepts, okay? And learning how the process works. If this video isn't sufficient, then I have other videos available in this, okay? I have other videos that the author even has videos, and I will make those available in our course. So you're going to have the techniques of getting what you need to know. It's up to you to watch the videos and get the content yourself. But by no means I want you guys to make a habit of starting on the homework and doing the quizzes and not watching these videos first. Okay? You might get by with it the first couple of weeks when we're doing the review content, but when we get into the new material for most students, it's going to be very difficult to jump right into the homework and doing the quizzes and without watching these videos. And my videos, these videos may not be sufficient to do it all automatically. You might have to watch another videos that I have available to you. And you definitely need to read the textbook. You need to read the textbook prior to actually watching the videos, because it's going to make the videos look a lot more. Even if you don't truly understand everything that you're reading, that's okay. You might want to read the textbook, watch the videos, and then go back and read the textbook again, if you don't think you have it down, okay? But just jumping right into the homework and the quizzes without, sliding by the videos and the textbook, you might get by with it for a while. But usually those students who do that all through the semester are not successful in this course, especially if you're just an average student. Okay, if you are very proficient in mathematics and you know your math really well, you might be able to get by with most of the course. But, if you're an average student, which is, I was an average student, and I would always have to read the textbook and take notes, and this is equivalent to taking notes. I had to do that, and I'm a math major. If I didn't read the textbook and write down everything the instructor said, I struggled. And I'm a math major. So just let that be your warning, okay? So, like I said, this is the first video. The videos hopefully won't be quite this long every time, but they will be quite lengthy. It's kind of going to be an equivalent to a course setting, okay? I hope everybody has a good semester and a very productive one. And until next time.